All right, guys, this is Chemistry Week 14. I am Mr. Hayden. You are here to learn. Just so you know real quick, I know it's being recorded, so only it'll affect the people today, but if your K-12 is down, just rechecking it until it does open up. I heard it just kind of pop back up. Don't stress about it. That's why you're in an independent study. You can do it at other times. So you're good. So we'll go ahead and get going, and let's have an awesome day. All right, so a few things to discuss. One is that some testing might interfere with some of your sessions in the next few weeks or so. We're going to be doing, like, especially 11th graders are going to be doing testing. And then also, I think there's like a science of some sort test or whatever. And then there's also, like, for 9th graders, PE testing, but there should be no 9th graders. Yeah. But just so you know, if for whatever reason a testing interferes with the live session, go to your testing and then watch your session later. Like, it's cool. It's fine. Am I going to get mad? Well, I might get mad at maybe Jordan, because I just get mad at her because she's my homeroom kid. But in general, I won't get mad at you if you don't come, because I need you to do well in your testing and really try and focus on that, okay? So we have about 6 weeks left. Someone just clap. Keep going. 6 weeks left and I hear it. Oh, there's your binder. It sounds like a clap, like you're all, yay, Mr. Hayden, woo! All right. You were clapping on the inside, you're staring at your hands going, if they were touching each other at a high velocity and the impact is and they made a sound, it would be clapping. All right, so we have 6 weeks left or so. I think it's like 5 or whatever it is. But we'll figure it out. Also, science notebooks are going to be starting being due May 11th through the 22nd as a 2-week window. I highly recommend just bring them to your live sessions, and I'll just grade them. Like, pretty straightforward. Like, just bring them and I grade them. Once I grade them, I put the grade in the computer, and you do not have to show it to me again. If you want to stop taking notes after that point, it's on you. You can stop taking notes. It's graded. It's done. I'm not rechecking at the end of the year. So if you show up on the 11th and you don't ever want to use your science notebook or do your science notebook again, that's all on you. But remember, you can use your science notebook for the final, which is cumulative, which means that how are you going to remember all these formulas? How are you going to remember all these examples? It's going to be more difficult than just remembering for like after for 1 unit. That's the reason why you use your science notebook. So you can access something that you wrote down. That's why it's there. And also so I can hopefully give you a free, lovely 100 points, maybe some extra credit if it's beautiful. It's really to help you in almost every aspect of your grade. 3 points by doing it, and you can use it on your test. Oh my goodness! You guys don't look excited about your science notebook. That's your excited face? Okay, there it is. There it is. I almost saw teeth. I almost saw teeth on the smile. She's like, not her phone for you. All right. So let's see here. Oh, 1 second. See, the people on the internet have more of a reaction than you do. Emotionless kids. All right, so is there anything else that we need to go over? Anything you can think of that you find might be important before we really get into this awesome chemistry? You're staring at me, and everyone looks confused, and then except Alex is like, hey. We good? I think we're good, right? All right, so we'll go and get going on the stuff for today. Okay, so by the way, I'm gonna try my best on it. Who here speaks French? You do? Okay, good. Just want to make sure. It's like the guy that we're gonna go over. Like I'm gonna try my best, but it's just gonna happen. I don't speak French. So you wanted me to say his name right? You wrote it in American. Just kidding. Just kidding. I just don't know French, so I'm gonna mess up it, but I'll try my best. Okay, so was that Chatelier? Chatelier? How do you say it? Chatelier? It's like weird. Liars. Chatty liars. Mr. Chatty liars. Was it La Chatelier? Whatever his name is, okay? You're basically, I want you to describe his principle. He was a French guy. He was pretty smart, came up with various things he can do to help with, obviously, pressure and how various things happen within reactions. So just make sure you write down this principle in your own words. I do not want the definition. If I want a definition, I can go look it up. I just go to Google and I type in, what is the definition of liars? And he was giving the answer. What happened to the here? You look up Chaplet lighters. Probably good. Yeah, what that you mean was yeah, that was fun. All right, so again, I do not want the definition. I want it written down here on words. So let's go ahead and get into a little bit. So his principle states, if a stress is applied to a system at equilibrium, the system will change to relieve that stress and reestablish equilibrium. It is like the undo button on your computer. So what happens is you have, like, say, a certain amount of reactants and it equals products. We've seen that before. We've been doing that. This plus this equals this. Well, what happens if all of a sudden you start adding more of the products or whatever, or if you start adding more reactants, or if you change, say, the temperature, or if you add pressure, or if you just do anything to it? It doesn't just all of a sudden say, oh, no, that equilibrium is good for us, it's fixed the way it is. It will actually want to rebalance back into equilibrium, and that is this principle. And we're going to go over a few aspects on how it occurs. So we'll look at these and we'll see. So give you a second to write those down. Let's walk around and stare at people writing stuff on their paper. People on the internet, you're more than welcome to type this stuff out as well. All right, so we're good. So you're going to see some examples of reactants, and then basically what happens is, how does it tip the scale? How does it get back to equilibrium? So if I add this, how would it go back to equilibrium? All right. So some of the factors that affect this equilibrium process. So if you had a company just sit there and it's perfectly set, and it's sat there and there's no more equilibrium, all the molecules can hit as many molecules as it can. There could be extra. Say you're doing sodium chloride, and you're mixing it with molecules of water, and you're adding other things. It could be completely dissolved perfect. Or there is a chemical reaction where they do displace. So maybe there's some left over. They don't all completely have a reaction. Some do, some don't. If you add more concentration of something, you have more reaction. Or if you have the temperature, if you raise it, typically that will increase the reaction. Pressure, by pushing them closer together, you usually get a reaction. And by the way, the reason why I say pressure is for gaseous systems only, because if I add pressure to a solid, it's not doing anything. Typically, if I add to water, it's not doing anything. It's going to go to a certain compression and just be that way. Okay, so this is only to gas because the molecule is so spread out. And then also the presence of a catalyst, and how that affects this reaction, or how it does in any way, shape, or form. Okay, so here's some of the ideas. Is that if you add more reactants, okay, so you add more reactants on the left side of the equation, what happens? Well, if you add more on the left to equalize, it will produce more products. It needs to equal out even. So and it literally is, if you think of a scale, that's good. I don't want to use that marker because it doesn't work. Let's try this one. Okay, so here's the scale. Okay. This scale's awesome. I know. If I was to add more, if I had more reactants and this pushes down, well, how do I equalize it? Well, I need more products. That's what that says. We will shift to the product. There will be more products being made because of the more reactants, and it will equalize again. If I remove reactants, well, it's not equal anymore. So what will happen is, by the way, all of these are reversible. Reaction is not one directional. So what happens, all those products will start to break apart and fill in the fact that there's reactants. They will equalize either way. Add more products. I'm sorry, add more reactants, more products. Take away products, more reactants. Make sense? How it shifts. Now the bottom part, if I add more product, it does the opposite of that. If I add more product to the right side, it will bounce. So the only way to bounce the scales is that some will break apart and fall and actually go towards the reactant side to raise that level to make it equal again. If I remove products, again, it will rise and then it shifts the other direction. Hopefully you can see it's almost like a fence. If I move one, it needs to equalize on both sides. One's jumping shift here. Don't know where that's. It makes sense, because if it doesn't, make sure you. Yeah, or is it just your teeth was really tangy? Sure. Spit your tea out. All right. Okay, so by the way, this is a formula in here that you're going to see in your K-12 class as well. It's the one just before this part here. Is that there's it was very similar to the equation at the bottom. I think it's like products over reactants. And what will happen is, you'll see this in K-12 where they'll give you moles. And the moles you have, you just basically plug that little mole number into whatever it says to. So it says, in this case, NO2 mole is equal to 0.8 moles. So you just literally plug 0.82 in there and square it. You'll see it. Hopefully you saw that, but if not, it was last Friday's work. If you need help with that, let me know. But the way it's written up here is Q is equal to NO2 squared. Now, how they get that squared is if you look at the product, this is 2NO2. This is 2NO2. Basically, you're taking that constant, the coefficient in the front of 2, and that is your square. If there was a 3 there, you would have a cube. If there's a 4, you'd have it to the fourth variable. Now the bottom one, there is no like number in front of the molecule. It's 1 mole. It's assumed to be 1 mole. So you only keep that down there, which is N2O4. And you put your products over your reactants, and that is equal to that equation. Now, this is a very simplistic form of it. We're not doing any moles and multiplication. You did that last lesson. So make sure you go back and look at that. If you need help with that, let me know. But what this telling us is that if Q is equal to K equilibrium, if it's equal to each other, it's perfectly equal. If I start raising one or the other, I'm just going to say one or the other, you'll start to see there's too many products or too many reactants, and you'll start to see a shift of equilibrium. This is just mathematics when I show you. If you raise one, it'll affect the other. If you lower the one, it'll affect the other. Whatever you do to this system, it needs to go back to another equilibrium. It needs to, it has to. So it's important. Not the whole world will just fall apart. That's how important it is. Okay, so temperature. So now I'm talking about an actual condition that can affect equilibrium. So temperature changes exothermic reaction. So consider heat as a product in the exothermic reaction of A plus B. They combine to equal AB plus, obviously, giving off heat. So if you add heat to this, it will shift to the reactant side. If you remove heat, it'll shift to the product side. So just write that down and know that, and that's how the reaction will occur back and forth in an exothermic reaction. It will be the opposite for an endothermic. So again, temperature can affect a shift. If you increase or decrease temperature, it affects the solution or whatever reaction you're trying to do. It'll either push it back or push it forward, depending on what you're actually doing. Good? So again, after this, I'm going to go back to any slide, just let me know, and I'll go back. All right, so an endothermic reaction, you see the opposite. Okay, so you actually see the switch the opposite. So in this reaction, you actually see A plus B, and you add heat, it creates the reaction or the molecule AB. So what happens in the change is you get the heat. So you add the heat, it will shift to the product. If you remove heat, it will equalize the opposite direction. It will actually shift to the reactant. Assuming my ad worked out as them. So it's the opposite of an exothermic reaction. So that's why you see the shift in the opposite way. That's really all it is. Maybe. Yeah. Okay. So pressure. So we talked about temperature. Now let's switch to pressure. So only affect equilibrium systems in an unequal mole of gas shifts, reactants, and products. Gas shifts. This is kind of a weird, like, we'll look at it, we'll talk, we'll write it down. It's kind of a weird process to think about. So in this case, if you increase the pressure, the stress of the pressure is this is what's going to make it confuse you, is reduced by reducing the number of gas molecules in the container. So if you increase pressure, the stress of the pressure is reduced by reducing the molecules. If it's too much pressure, you have to get rid of some to equalize it. It's reduced by reducing. You like that? It's reduced by reducing, the reduction of the reduction of the reducing. Like too many words are the same. All right, so we good? Okay. So, in this case, there are 4 molecules of a reactant, and do you see how there's 4? Where are the 4 coming from? Oh, bring some down. Bring some down. No. What is it? How do I know there's 4 moles in the reactant site? Use your brain. On the left-hand side, on the reactant side, moles would be those coefficient numbers in the front. So there's a 1, technically. It doesn't say 1, but it assumes. Just like if X is there, there's an assumption of a 1 in front of it. And then you have your +3. There's 4 variables. You get 2 molecules of product on the right. So the reaction will shift the product to form an ammonia to equalize. Okay, I just want to go over, let me see, is this it? All right. So on the last one we talked about, your list that you had at the very beginning was catalysts. Catalysts themselves lower the activation energy. We talked about that last time. It doesn't take as much energy for the reaction to occur, and it increases the rate of reaction. It will lower the forward and the reverse reactions. It will lower basically the energy needed for that. Therefore, a catalyst has no effect on the equilibrium. It just speeds it up to reaction. It just gets it there faster. So if I put 2 together, and in a normal sense, it takes 2 weeks for it to completely have all the molecules finally bounce into each other and create the solution or create the product. If I add a catalyst, whatever it is for whatever substance it is, it can speed it up and happen within minutes. So all it does is speed up the process, doesn't actually affect equilibrium, it gets it there faster. Okay? Now, if I start adding stuff, and we're going to see a few examples when you start adding stuff. We're going to look at it and we're going to break it down and see how it does affect it. So if we insert a substance, is a substance that is not inreactive. So if you look at it, is the substance you put in, is it going to react with any of your products or your reactant? Or you're just putting it in there and it really does nothing. Like if I add salt, something that does nothing react with salt in this thing. I add salt, just add salt, nothing's going to happen. That's why sometimes if you add, I know someone was telling me, well, I added a whole bunch of chemicals from the box and nothing happened. Because you added a whole bunch of stuff and there was no reaction. You just added a whole bunch of inert substances together. They aren't going to do anything. Good job. All right, so let's use a few examples. So, okay, looks like a lot of stuff, but let's take it bit by bit. Let's chunk it. So, S8 is a gas, plus 12 oxygens, which is a gas. It is a reversible, it goes back and forth. It's a reversible equation. It will equal out to 8SO3, it's a gas, plus it gives off energy. So real quick, let's make sure it's balanced. How many S's on the left? There's 8. How many S's on the right? 8S is 8. Okay, 24. There's 24 on the left of the oxygens, 12 O2s, and there's 8 O3s, so there's 12. Yeah, 24 on the left, 24 on the right. We're good. 3 4. You guys see that? By the way, this is last year, so for last semester. Hopefully you know this. If you don't, talk to me when you can balance equations together. So what will happen? So if I add oxygen to this equation, what did I add it to? Where's the oxygen at? Is it on the reactant or the product side? Where's the O2 at? Okay, what side is that? The reactant side. Very good. It's the reactant. So what will happen if I add a whole bunch more there? If I add more reactants, they'll react more, and what will happen? There'll be a shift to the product. The product will have to increase equal. Does that make sense? No, it doesn't make sense enough. Be completely honest. We're cool. Just you and me here. Okay. No, I like that. Just don't tell me. Okay, so if I added this because there's a bunch of ethane left over, just kind of chilling in the solution. Well, if I want those to react, the only thing to react with is oxygen. So if I add more to there, they're going to react. And where do they shift to? They become a product. So you'll see an increase in product to help equalize if I add more oxygen to the side. So we'll go through, we'll see a couple more times, and at the end, if you really make it, that's fine. Don't even feel weird about that. Just tell me, hey, that doesn't make sense. I'll go over you. That's what you're supposed to do. If I didn't know something in high school, okay, I don't know what you're talking about. Okay, whatever teacher it was, like, I'm sorry, you made no sense. Like, you really said that. Now, if the reaction is cooled, and this is just random stuff, if it is cool, it will shift to the product. That's fine, let's get past that. Size of the container, we'll get past that. Okay, so this is sulfur trioxide, the 8SO3. You see that? You see the 8SO3 on the product side. Now, if I was to think of this, there's that on one side of the wall, and those, S812O2 on the other side. Now, if I took some product away, is it equal? No. What has to happen for it to be equal? They need to react. There's a shift to them to react, to equalize. That's why it says it shifts to the products. The reactants will shift to the products to replace it. You take it out, it replaces it. If I take water out of the cup or out of this area, it will equalize it. It has to. If I leave it there, it's equal. They're fine. As soon as I take some out from the product side, the reactant starts to go, and they slide in and they sulfur trioxide. So, got that? Okay. Same thing, but the opposite way we were thinking. If I had a catalyst, there would be no change. It would just happen faster. No change. No change, no change, no change. So here it is again. So I'm going to add, this is 2 NaHCO3 solid. It reacts to create a Na2CO3 plus H2O gas plus CO2 gas. Good for us. So if I add if I take out carbon dioxide, so where's carbon dioxide at? Is it on the reactant side or the product side? CO2. It's on the. Thank you very much for everyone else that was like, whoop. You're on my clock. Good question. I'll tell you a question. All right. All right. So if if I took CO2 out, now it's not equal. There's going to be more reactions taking place to fill in the fact that it needs to be done in the CO2 in this reaction equals. So there'll be a shift to the product to replace it. Now, if I add sodium carbonate to this, there's a little weird thing. It says solids, they do not affect equilibrium. So if I add solids to this, I didn't write this. It says 2. I know it. It's over. I borrowed this one. Professional. I need a total reference to that. I don't. But no, let me see here. Our comment was removed. Again, solids don't affect it. But there's a weird one. This is the one that it took me a second to go, wait, let me look at that again. So if calcium ions are added, so I add calcium ions to the right, it will react and actually shift the opposite direction. It'll go back to the reactant. So it added the ion to the calcium, Ca2+, that's a calcium ion. If I add stuff to that side, remember, I have too much on that side, it'll kind of level out by switching going to the reactant side. I'm adding NaOH. This is weird stuff. I'm sorry. This one's like the only weird one, so try to follow as best you can. So if I add NaOH, it's basically OH negative. So what I did is I actually added that very last one, OH negative. And I added more of those. If I add more of those again, it shifts to the reactant to help kind of like go the other direction, stay equal. Now the weird one is the bottom one, or the bottom two. That one took me a second. I was like, wait, what? So if I add HCl, I technically added H positive. Well, if I add H positive, you know, I want to add to the OH negative to create water. So I actually removed part of the product to turn it into water. What will happen is there'll be a shift to the product to help fill that space I just made in the water. I'll just look at this, okay? It's two different thoughts in the same model. It's understanding that HCl will break apart and create hydrogen ions. Basically an acid. And now there's OH just chilling there. Maybe one positive wants to hang off the one negative. So they get together and they make water. Well, now that's water. That's not OH. It goes away. If there's water, goodbye. Well, I need to fill that back up, so I need to have those react more from the reactant to the product side to fill that space again. And hopefully not add any more HCl. So example, if I had this, I don't know what the equation really is. I'm not a chemist, so I'm trying to pretend I'm a full-on chemist. But say this was a bad reaction that created a base that's not good. And I wanted to say make something good out of it. I could add the HCl to it, and I at least get water as a byproduct. Then I can start breaking it down to the water. So. Same thing, NH3PO4. Now the PO4 ions will want to hang out with those PO negative ions and merge together. Will those go away now? I need more reactants to react to fill in the space. So there'll be a shift to the reactant. That makes sense. Good? Okay, guys. Any questions? People on the internet, you can go ahead and take off and go ahead and put this terms you can talk about. I recommend talking about when you're doing your discussion or you're doing your definition. Bring up pressure, bring up temperature, bring up the various parts that you understand and put that into perspective for other people. So I'll go and shut the recording down. If you have any questions, I'll be on to have you ask.